Urban air pollution is becoming one of the intriguing concerns in the developing countries like India and many other Asian countries. So, to manage the urban air pollution, modeling is one of the important tool to predict the source contributions and to predict the air pollution levels at various places, and also to analyze those data and come up with some suggestions for the air quality management. Basically, modeling is being carried out across the world, particularly in United States and many other European countries, to manage the air quality of an urban setting. The models can be of different types, namely physical, experimental, empirical, and statistical. In predicting the air quality or in predicting air pollution sources or in predicting the air pollution concentrations at a given location, there are a number of models applied worldwide. But mostly these models are mathematical and numerical techniques. And the model simulates the physical and chemical process of air pollutants as they disperse from a given source. And based on the inputs of meteorological data like wind direction, wind speed, and the lapse rates, atmospheric stability, and the source informations like the stack height, emission velocity of the gas, and also the heat of the gas that is being emitted from the stack. Based on these parameters, the model can simulate the concentrations of the air pollutants in a given or in a receptor location. Basically, these models are designed to characterize the primary pollutants that are emitted directly into the atmosphere. And in some of the models, even the secondary air pollutants that are formed as a result of a reaction between the primary pollutants are also possible. So basically that across the world, there are two types of models that are being widely used. The one is point source dispersion modeling, another one is receptor modeling. Point source dispersion models are typically used in the process to estimate the concentration of pollutant at a given location in the ground level receptors or surrounding an emission source. The point source is nothing but from the stack, you can really predict or model the concentrations at a receptor locations. What sort of pollutants or what concentration of the pollutants will be there at a given receptor point. So this is nothing but we have a known source of stack, and the gaseous emissions from the stack are already determined, and then based on these emission parameters plus the meteorological parameters, a mathematical equation is developed to model the concentration of a pollutant in the downward wind side or the plume or the downward plume or the plume that travels in the wind direction, the wind trajectory. In the trajectory location, in the trajectory we can model the locations, the pollutants, whereas in the receptor model are mainly based from the ambient concentrations. Receptors, this is another kind of model where the pollutants or the concentration of pollutants in a given location is being monitored, quantified by various techniques using the measurement equipments like PM10 samplers or gaseous sampling units. And the source, in this case, it's like just opposite, where the source is determined from the data which is obtained from the ground level air quality monitoring stations. That is based on the ambient data, we try to predict. So a source model uses the source emissions as inputs and calculates the ambient concentrations, whereas the receptor model uses the ambient concentration as inputs and calculate the source contribution. It's just the reverse. So it's clearly shown in the picture here. The source model, you can see the known source emissions and known dispersion characteristics. So these are the two parameters that are given as input, and it will estimate the concentrations at a desired receptor location. So we can just predict the concentrations at a downwind direction, maybe 1 kilometer, 2 kilometer, or 3 kilometer, whatever it may be. Whereas in the receptor models, the ambient air pollutant concentrations are known through the monitoring stations or the data from the instruments that are used to monitor the air quality. So like PM10 or SOx or nitrogen dioxide, whatever it may be, the pollutant, these are given as input parameters. And the source characteristics or the source profile or the source signature is there already, that is being calculated for certain source profiles. Like for example, if the gasoline is being burnt, what sort of pollutants arise from the gaseous pollutant, the gasoline, are all known, and these have been already derived. And using such known source profiles, we can estimate the source or the source for the pollution in a given location. So data from the receptor location is used to identify the source and also the quantify the source. So let us get into the point source model. Point source model, as I told you earlier, it predicts the concentration at various locations around the source. It is mainly towards the downwind direction. Identifies the source contribution to air pollution area. It assesses source impacts and suggests the control strategies. So these are the main usage of this model. It is mainly used to predict also the future concentrations. If at all there is an industry coming up in an area, what could be the concentration in the downward wind direction or in a given location. So basically, the air quality model is a mathematical relationship between emissions and the air quality that incorporates transport, dispersion, and transformation of compound emitted into the air. So the model is basically a mathematical equation which requires the input parameters like the emission parameters, as I told you earlier, and also sometimes the model parameters like the source profile and the meteorological parameters like wind speed, wind direction, atmospheric stability, dispersion coefficients. These are the parameters given as meteorological inputs, and then the air quality in a given location will be predicted by the model. So this is a broader picture of the air quality models that are being used and the principle behind it. So basically, we can classify as deterministic, statistical, and physical models. And the most widely used is the deterministic model, and which is again the steady state model. and in which the Gaussian plume is the most widely used model across the world. And there have been various models available now based on the Gaussian plume. In the statistical model, and again in the deterministic model, you also have the box model, grid model, spectral, puff, trajectory, and lag, and Eulerian and Lagrangian models. So all these things are based on the mathematical equations. And there are some statistical model which the kind of receptor models like principal component analysis, positive matrix factorization, and multivariate analysis also are used to determine the air quality sources or source apportionment. And also there are physical models that are being which is I think it is rarely used, but most of the models are based on the Gaussian plume model. So a deterministic model calculates the pollution concentration from emission inventory. The emission inventory, as I told you earlier, for example, the emission inventory of the coal industry or a cement industry is known. The gas or the plume that is coming out of the stack is widely known for its nature, and it is being already classified based on the pollutants like sulfur dioxide, nitrogen dioxide. So the emission the model is mainly based on such emission inventory and the meteorological parameters, which is considered as steady state, or the model considers the most of the meteorological parameters in a steady state, like wind speed is constant throughout the model, and there is no change, and it doesn't it assumes that the model is the wind speed is constant throughout the analysis. So deterministic modeling is a traditional approach for the prediction of air pollutant concentrations in urban areas. So this is as I told you, this is the Gaussian dispersion model. It was developed in 1800s, and it has been updated and modified several times, and several people have modified it, and even it is subjected to modification, and recent versions are available based on the Gaussian plume model. So the Gaussian plume model, as shown in the picture, it has got, as soon as the plume or the flue gas is out of the stack, it tries to move towards the downwind direction, or the windward side. So that direction, is called as x-axis. The movement of plume towards the wind or the downward wind direction is the x-axis, and then the horizontal movement of the plume, it is given here from the stack. As the plume moves, it spreads horizontally. So that axis is called as y, and then the plume also spreads vertically. So that is the z-axis. So all the three axes are perpendicular to each other. X-axis, y-axis, and z-axis are perpendicular to each other, and there is a central line in the plume. So this considers the model considers the gas transported downstream. Dispersion in vertical direction is governed by the atmospheric stability, and the atmospheric stability is a natural phenomenon, and the atmospheric phenomenon, which I'll come to it later. The vertical movement of the plume is mainly governed by the atmospheric stability, whereas the horizontal movement, that is y-axis, is governed by the molecular and eddy diffusion. So There are certain coefficients arrived for this under the constant conditions. So the x-axis is oriented toward the wind as mentioned earlier. So the concentrations are assumed as symmetric about x-axis and y-axis. So you find that on the both sides it is symmetric. The distribution of the pollutants are symmetric. So this is another picture, and as I told you earlier, Z, Y, and X are all perpendicular to each other, and as the plume moves towards the wind direction, windward direction, the diffusion or the dispersion happens in all three directions. So these are some of the models which use the Gaussian plume model, and this has been taken from the US EPA website. You can see the models are ADAM, ADMS, like that. So many models are now available based on this Gaussian plume model. And I cannot tell all are based on Gaussian plume, but most of them are, these models are based on the Gaussian plume model. So the computer software parameters include the pollution emission rate from the stack, that is grams per second, the stack height, then the stack inside diameter, that is the exit diameter. So the gas temperature, that is, it is important to analyze the heat transfer. So the temperature of the gas and the velocity of the gas and the ambient air temperature, then the receptor height, topography, etc. are the parameters that are being used. So this evaluates the pollutants at a given location. So for what all source types these models are being used? These models are used for a typical point source like the stack which you saw in the picture. That is a single emission point from a smokestack with continuous emission rate, and also the volume source, user sets height, virtual. So this is like a virtual point source. Also we can generate the data for it, like the railway line, conveyor belt, and all these things. And it can also be called as a line source, whereas where a particular highway where you find the movement of the trucks or typical kind of cars. So we can also use this Gaussian plume model to predict the concentrations or to predict the pollution dispersion from a line source. And also it is also used to predict the area source and also the open pit emissions from an open pit, from a mine or quarry, and also from the flaring stations, like any kind of flaring stations where the combustion of like incinerator or LPG or the waste to gas flaring, like that. So again, coming to the same parameters, these are the two basic parameters that affect the dispersion. That is, the source emission rate of pollutants is always considered constant, but it is in real world sometimes there may be change. The stack height is constant. The exit velocity of the gas is also likely to be constant. The exit temperature of the gas is also is likely to be constant. The stack diameter and the meteorological conditions, the wind velocity, wind direction, ambient temperature, and atmospheric stability. But the model assumes that Gaussian plume model assumes that it is steady state conditions, like the constant source emission at strength. There is no change in the gram per second of the pollutants while it is being emitted into the atmosphere. The model considers it as a constant. So if there is any change in the strength of the emission, the model cannot predict it. So the wind speed, direction, and diffusion characteristics are considered as constant. The mass transfer due to bulk motion in the x direction far outshadows the contribution due to mass diffusion. So, and also the conservation of mass, that is no chemical transformation take place. That means the pollutants within the plume does not react to each other and it remains inert. The model considers that it remains as such from the source to the receptor location. And also the model assumes that wind speed is above. Our model works out only for the wind speed above 1 meter per second. And also most of the models are limited to the 2 kilometer from the source, and beyond that the model cannot predict the correct concentration. So it is limited to. So this is how the equation is developed based on the Gaussian plume model. And equation for the Gaussian plume model, this is the height of the stack is h. It is normally the small h, and as the plume rises to a certain extent, and then it travels towards the x direction. So the topmost height, or it is where the plume starts traveling towards the x direction. So that is called as effective stack height. That is the plume that is released from the stack moving towards certain height and then dispersing towards the x direction, downwind direction. So that point is delta h, and small h plus delta h gives you the effective stack height. Sometimes effective stack height is considered as constant. It is like the stack height is known, h is known, and the h into 1.73 is considered as the effective stack height, that is he. That is, as you said, that is delta h plus h. The delta h is the plume rise. The plume rise sometimes is considered as h plus 1.73h. So here in the picture here you can see, as it moves towards x direction, the pollutants get dispersed and the bell-shaped curve enlarges as it goes towards the x direction. So the dispersion happens, dispersion from the source towards the x happens horizontally mostly, and also the vertically. So as the distance increases, so does the dispersion. So at a given point, you have the values. So this is the equation, and here the xyz, the C is the concentration at xyz, and the first formula, that is q by 2 pi, and u is a wind direction of standard deviation, that is a coefficient, dispersion coefficient. I'll come to that later. And this equation gives the concentration, the center line of the plume. If you take a cross section of the plume, the center part of the plume will have highest concentration of the pollutants, and this gets dispersed vertically and horizontally. So the center line, so this particular equation predicts the concentration at the center line of the plume at a given point x. And whereas as you move sideways, that is y direction, So the direction doesn't matter. It can be x, y1, y2, or y like that, either side. So this is the equation that predicts the the horizontal movement of the pollutants. If you are interested at y2 or whatever, you can. This is the equation for the horizontal movement, and this is the equation for the vertical movement of the pollutants. So this sigma y and sigma z, the coefficients are actually arrived based on the the diffusion parameters, which is like it is available in all the air pollution textbooks. We can based on the atmospheric stability, we can actually get the coefficient values, which I'll come to that later. So you can have all the three equations at whatever is the desired location. For example, you may be interested only in the center line of the plume. So this is the formula that is used for the center line at a given downward wind point. And for example, this is a small example. A factory emits 20 gram per second of sulfur dioxide at high tide. The wind speed is 3 meters per second. At a distance of 1 kilometer downstream, the sigma y and sigma z are 30 and 20 meter. This 30 and 20 meter is normally given. Otherwise, we can, based on the atmospheric stability, or it can be easily taken from the graph. And I'll show you that graph. So what are the SO2 concentrations? This is a question. What are the SO2 concentrations at the center line of the plume at a point 60 meters to side and 20 meters below the center line? So the concentrations at the center line also is required, 60 meters to the side and 20 meters below the center line. So here is the values, and you apply here, and you get you try to calculate it at 60 and 20 meters, and you get the values here. That is this is the value for the at a given point at x, whereas in the x, if this is a ground concentration, so the z and y will be 0, 0. So this is the concentration at the ground level at the desired point, whereas the center line is y and they are 0 because we are only measuring the ground level concentration using this equation. So as I told you, the valuation of standard deviation of y and z are actually based on the atmospheric stability conditions. And let us, I can show you the stability. Stability class is A, B, C, D. If it is extremely unstable, it is A, B, C, D, and E. So how you come to this conclusion? This is like based on the solar the solar elevation, that is the solar radiation, and the time when the measurement or the Gaussian plume is applied. For example, if it is above 60 degree from the horizon, it may be a little difficult to understand, but you can consider that probably during the afternoon time you get very high solar radiation. So the solar inundation, or that is like, if the angle is above 60 degrees, then it is considered as strong. So based on these classes, it is whether it is between the solar radiation and also again the wind speed. So based on these two, there have been Um, we can find out the, for the x and y is that. So here you can see the, from the figure 4 to 7, x is 500 meters. So that this is the diffusion parameter, which is um, arrived using this table, that is the stability class, whether the atmosphere is stability, and how do you define the, and this is another equation that is being used to calculate the effective stack height, the plume rise, and this is again based on the, the stack velocity, then the heat emission rate and the wind speed. So based on this, we can calculate the delta H, that is the plume rise. So here there are some of the examples of, if it is a neutral atmosphere, this is the stability coefficient. So here, this is a sort of atmosphere where there is an inversion layer. This is the lapse rate. As the altitude increases, the temperature decreases, but at some point of time, there is a temperature inversion. As you go higher and higher, there may be an increase in temperature. This is normally it is called as inversion layer, and since the layer is very warm, the pollutants cannot disperse vertically, so that it gets trapped here in this layer. So, and similar thing occurs in the valley also, and this is how the plume behaves based on the lapse rate. That is the adiabatic lapse rate and the environmental lapse rate. R is the environmental lapse. The vertical movement of the plume is affected by the lapse rates, and there is a dry adiabatic lapse rate and wet adiabatic lapse rate, and if there is an inversion in temperature, and these lapse rates are highly affected, and it determines the movement of the air pollutants. So this is plume behaves if like this, if there is adiabatic lapse rate is more or less equal to the environmental lapse rate, and if there is an inversion, temperature inversion, then the pollutant doesn't come down, and it remains like, it is called as fanning. So this is how pollutant behaves during the inversion. And this is again fumigation, where the layer of which we saw earlier, where the temperature suddenly increases after some high altitude, and the pollutant, there is a vertical movement, or the vertical dispersion is totally affected by this phenomenon. And this again is like, if the temperature or the inversion happens at the ground level, then this sort of behavior can be expected. So, but the Gaussian model does not take into account all this. It assumes that source pollutant emission rate are constant, steady state, constant wind speed, constant wind direction, and the atmospheric stability class is also taken as either one thing, that is stable, stability class A or B. It is not that a plume experiences all these classes. And pollutant mass transfer by primarily due to the bulk air motion in the x direction, and it doesn't take into account if there is a kind of obstruction or a terrain disturbance, and no pollutant chemical transformation occurs. That is, pollutant A and B doesn't react each other and form another chemical, and it takes that everything remains constant. And so all these conditions, like the stability at one point is different and atmospheric stability at another point is different, and the Gaussian plume model at times does not take into account. And now there are some more Gaussian plume models which also considers the terrain correction, Egan terrain corrections, like if there is a mountain nearby, so you can apply a different equation which corrects the terrain, and also the building. If there is a building, then there could be a swirl wind or something which would affect the plume behavior. So this is also taken into consideration in the recent models. Now coming to the receptor models, as I told you earlier, receptor model takes the ambient concentrations in a given receptor location, and it tries to identify the source contributions or the source profiles. So this is mainly based on the mathematical models and the statistical models. So in this case, the input parameters like the ambient concentration CI, and then uncertainties, source profiles and uncertainties, ambient concentrations and uncertainties, source profiles and uncertainties. Output is the source contributions and uncertainties. So here, the chemical mass balance is one of the commonly used receptor models. And this model quantifies the contribution using the chemical signatures, characterizing the source types rather than the contribution from individual emitters. So the CMB model uses the chemical composition of the ambient pollution samples to estimate the contribution of different source types to measured pollutant concentrations. That is, actually you get a set of values in a location, set of pollutants or the levels or the concentrations of pollutants, and we try to identify or match with the source profiles which are already available, and then finally come to a conclusion that this could be from these sources. For example, if you find the sulfur dioxide in a location as 80 microgram per meter cube, and based on the model, we can identify that this particular mass is from the industry which, or the kind of emitting sources, probably a coal-fired power plant or something like that. So actually these are the instruments that are being used at a location to monitor the ambient air quality. It may be PM10 or PM2.5 or sulfur dioxide, anything. These are the samplers that are being used to find out the concentrations in a location. And these are the source profiles. The source profiles or the emission inventory. These are like from the emission sources we can identify. For example, if there is what kind of sulfur dioxide, or what kind of what amount of nitrogen dioxide, or what amount of particulate matter is being released from this kitchen or from an industry or from a vehicle. So these are all actually inventoried, and these are used as a source profile. You can see the emission testing, and based on this can serve as an input parameter. So this is a typical the kind of graph which is being generated in the chromatography mass spectrometry, as if a gasoline engine, these are the compounds that are emitted out from the gasoline powered vehicles, and These are the kind of chemicals or the carbon compounds and their concentrations or their at for example, even the source profile is available for the road dust. If you have all these compounds in your ambient concentration, we can figure out that this could be probably from the road dust. Or if you find this set of compounds in your receptor location, we could figure out, or we could conclude that maybe this is from the diesel source. So this is how a chemical mass balance works out. You can see the like the different sources are given here: industry, transportation, vegetation burning, geological, marine, secondary organics. So using a chemical mass balance model, we can identify from the given concentration at a location, we can identify these are all could be the probable sources. For example, in Asia, the 40 percentage of sulfate is from the sulfate is secondary ammonium sulfate from the PM, and then only 3 percentage is from the transportation, and 10 percentage of the PM 2.5 mass is from the industry. So this chemical mass balance model can predict the source concentrations like this. It's very useful to determine the sources in an area, and appropriately the management measures can be taken using this data. A similar such model is positive matrix factorization, and this is also again a multivariate analysis tool. Almost it also gives the same kind of results. The EPA, the Environmental Protection Agency US, has developed this model, and actually this model needs huge, can be applied when there is a huge set of data, and it normally requires a large data, and from the large data again it can identify the same kind of source profiles, and we can find out based on the ambient concentrations, and we can derive the source, whether it is industry or road dust or power plants. We can easily determine the sources by using the PMF analysis, and it is the software is available in the US EPA website. You can download and attempt computing the sources by using a different set of data. And the source contributions are used to determine how much each source contribute to a sample. For example, this is again the PMF analysis can also easily find out, even within the a source, it can even find out what sort of source, whether it is from the tire wear or the resuspension or exhaust emissions. So the emissions depend upon all these parameters are taken into consideration while calculating the contribution from each source. So this PMF gives a kind of values like this. So based on this this value, we can come to it. It gives different factor one from a set of data. We get the factors like this: factor 1, factor 2, factor 3, and it can be, maybe the factor 1 can be the vehicular pollution that is given in blue. In this each circle different denotes different places. For example, in place A, the pollution is mostly from the vehicular emissions, And here also it is likely from the vehicular emissions, whereas the orange can be of industry and the green can be of agricultural burning. So PMF analysis gives an idea of each and every source, and it also the quantifies, or it gives in percentage how much is the quantity of pollutants from each sources. So again, another mostly widely used model is the principal component analysis. This is again a statistical tool. It is also used for data reduction. The statistical method is used, it is actually based on the covariance matrix from the given set of data. For example, in a location, if you measure ambient air quality, and also if you measure different kinds of heavy metals, for example, copper, lead, iron, chromium, cadmium, etc. And if you try to analyze using a PCA, the it like the output will be like a set of it. The PCA gives you a set of values, and from which we can interpret the sources. That is, in a system with multiple input variables, this approach is used to determine the variables with greater eigenvalues, that is, eigenvalues more than one, and further identifying the core problem. For example, this is like a PCA identifies a set of components, that is, component factor 1 may be one component, one group of components, factor 2 may be another group of component. And based on this separation, or based on this identification, we can come to a conclusion that this phenolphthalein or benzoyl, this set of combination is from the diesel vehicle, and this set of combination is from the LPG vehicle, or this set of combination is from the kitchen. So this PCA is an easy method which is being widely used to identify the source. So that's all we have for today, and this is the most commonly used models for the air quality. Thank you.